Okay, hello everyone. Let's continue on. So we're going to now find how much percentage of the aspirin tablet is carbon, hydrogen, and oxygen. So let's use the mass of the aspirin tablet to calculate the percentage of each element. So since the mass of aspirin is in milligrams, we will have to convert the mass of aspirin to grams. So we know it's a 3 milligram sample. So we're going to write 3.00 milligram aspirin. So let's just convert this to grams just to get practice with our dimensional analysis skills. Okay, so that's how much aspirin we have. So going off the results of our analysis here, we're going to write, for carbon, we're going to write 0.0018015 over 0.00300. So let's put our units here. Times 100. So if we do that calculation, we will get, let's see here, 0.0018015 divided by 0.00300. And that's roughly 60.0 percent, or 60.1%. Let's just write 0.1 for 3 sig figs. Okay, 60 point. So let's write out maybe the whole number first. So the whole number is 60.05, but we want to round to this third digit here, so we're going to write 60.1% carbon. Okay. So now let's kind of scoot this over a bit. So let's scoot this up a bit so I have room to calculate hydrogen's percentage. So hydrogen is much of the same thing, but we're going to replace the top value in our calculation and replace it with the value for hydrogen. So we're going to have 0.00013451118 grams over 0.00300 grams for the aspirin. Okay, and then we're going to multiply this by 100 to find our relative percentage of hydrogen. So if we do that calculation, we will get 0.00013451118. And if we multiply that through, we get 0.0448. Oh, sorry. I should not put the percentage, the decimal point. We get 4.4837.3. So I wrote some extra digits, but we're going to round to this digit here for 3 sig figs. So we get 4.48% hydrogen. So one other way you could convince yourself that this is the right mass of hydrogen if we knew the formula for aspirin, but unfortunately we don't. But if you were to look it up, the formula for aspirin, and just calculate the molar mass, and then calculate how much carbon atoms there are, find that mass divided by the molar mass, you should get a value roughly close to what we just calculated here from combustion analysis. So that's how we know, like, That's how we know we're right, because the molar mass and its relative percentage is also has the right percentages. Okay, so now let's figure out. Okay, we figure out carbon, hydrogen. What about oxygen? How does oxygen come into the mix? So the thing about oxygen, you can't calculate oxygen directly. You have to calculate it indirectly. The reason we can't calculate it directly is because when we're when we're combusting our sample, there's an excess of hydrogen gas. So if we kind of screw up here, again, looking at our picture, you see here there's O2 gas coming to our sample. So that's not the limiting reagent. The flow of oxygen gas in the furnace is going to be our excess reagent. So we can't really find out how much oxygen is in the sample directly using either H2O or CO2. We actually have to do it in a different way. So the way we do it is we take our masses here. So let's combine our masses. So we take the mass of oxygen. We're going to take the mass of aspirin minus the mass of carbon plus the mass of oxygen. All right, so the mass of carbon, mass of oxygen in sample. In the sample will tell us, and we take that difference from the mass of aspirin, our sample, we're going to figure out the mass of oxygen. Oh, sorry, not mass of oxygen. Sorry about that. Hydrogen. So this will equal our mass of oxygen. Okay, so if we do that, we will get 0.0300 minus 0.0018015 minus 0.000134511. And if we do that calculation, we could write the sum here, and let's do it in our calculators. 0.0. I don't think it's 0.0. Oh, sorry, I messed up here. It should be an extra 0 here. 0.00300. Yeah. Minus 0.12313451118. So if you have a negative number, that means you messed up. We messed up somewhere, and we should go back and check our math. So there should not be a negative value. So we get 0.00010 639.882. So since all our values had 3 sig figs in them originally, we're going to keep it to 3 sig figs. Or actually 5 decimal places. So 1, 2, 3, 4, 5. So we're going to underline it here at 6, right there. That's where we would round. Okay, so now we're going to use, this is the mass of oxygen. Okay, so now we're going to use that mass and figure out the percent oxygen. So oxygen equal is right here, 0.0010639.882 grams over 0.00300 grams times 100. And let's see what we get. So we get 0.0010639.882 divided by 0.00300. So I would write the extra zeros out just to get you the hang of significant figures. If you don't write it out like that, you might forget about the sig figs. So we don't want to forget about the sig figs. Okay, so we're going to get roughly 35.46627. So let's just keep those digits right there. And then since it's multiplication, we're going to do 3 sig figs. So we should round it to this digit, the 4 here. So we're going to say 35.5%. Okay, so now if we add all those values up, all the percentages, they should give us close to 100%. It might not be exact because we rounded, but it should give us, roughly 100.08%. So that's pretty good. So that's how you would do combustion analysis. So that's one of the key kind of problems in this chapter, doing combustion analysis for any compound. So you can expect this one of these types of questions, like maybe this type of question appear on the exam as a free response. So it kind of encapsulates everything really. Chemical formulas, molar mass. Well, not chemical formulas per se, but molar mass, mole conversion to grams, moles to grams, and then doing sample analysis. Figure out percent composition. I think that's important. It's an important concept to talk about. Okay, so that's how we figure out like how much carbon, oxygen, hydrogen are in the sample. We can also do other atoms as well, but usually most of the samples, that really occurs in nature, most of them are purely CH oxygen. Molecules that only contain carbon, hydrogen, or oxygen. Sometimes we have nitrogen in the mix, and then also sulfur. But usually, in this case, when we do combustion analysis, we tend to just focus on carbon, hydrogen, and oxygen. So those are probably the examples we'll see. Okay. So let's go on to the next example here. All right. So we know that methane is once known as marsh gas because it was collected above certain swamps or marshes in Britain. So we know it's 74.9% carbon and 25.1% hydrogen by mass. So if a 100-gram sample was collected for analysis, let's find the empirical formula. Right? What is the empirical formula for methane? So this is a formula. Sorry about that. So what's the empirical formula for methane? So first, we determine the mass of hydrogen and carbon in the sample. So if it's a 100-gram sample, right here, so 100-gram sample times, so for 100 grams, we're going to represent the percent as a fraction. So 74.9% is 74.9 grams of carbon per 100-gram sample. So we can simply write it as, these numbers will cross out, and we get 74.9 grams. Grams of carbon. Like that. Okay? So we do the same thing for hydrogen. So we have 100 grams. So these exercises are designed to help students work through the problem and really show their kind of quantitative and qualitative reasoning towards getting towards the answer. So doing these problems are essential to doing well on the exams. So my exams, they'll be very, let's say, they're kind of split between like how you're tested. So some questions, some parts of the exam will be multiple choice, fill in the blank, vocab sometimes, concept questions. And then the free response is like problem solving is a big part of it. So that will be like the last part of the exam, and it's roughly around maybe 25 to 33% of the exam. So I try to make each section like an equal amount on the test. But anyway, 100 grams times 100 gram sample. 100 gram of the sample, we're going to have 25.1% grams hydrogen per our sample here. And we see that crosses out, and we get 25.1 grams of hydrogen. Okay. So now we need to convert the masses to moles. So in combustion analysis, we were converting grams of carbon dioxide and water to first moles, and then to moles of the single atoms, and then to grams. But here we're going backwards. We're converting from grams of our elements to moles of our elements, and then we're going to see what's the ratio of moles and figure out the chemical formula, or in this case, the empirical formula, like what we talked about last week, the formulas. Okay, so for carbon, we have 74.9 grams of carbon times 1 mole carbon is 12.01 grams. Okay, so if we do that, we will get 74.9 divided by 12.01, and we get roughly 6.2365. So let's just keep a few extra digits here, but if we did round, we would underline this digit here. Okay, and then we have hydrogen. We have 25.1 grams hydrogen times 1 mole of hydrogen, 1.01 grams hydrogen. Okay. So when we're going from grams to moles, we're dividing moles to grams, multiplying, and that should be evident in how you set up your fraction here, or your conversion factor. You want the units, what you started with, to cancel out, and you're going to end up with a new unit. So in this case, we have moles carbon. Okay. So for hydrogen, 25.1 grams divided by 1.01, and we get about roughly 24.8515 mole of hydrogen. Okay. So to figure out the empirical formula, we need to determine the ratio of carbon atoms to hydrogen atoms, and the only way we can do this is through the mole. We can't do it through grams, because 1 gram of carbon is not equal to a gram of hydrogen, because they have different molar masses. So we have to do it on the mole scale, where we're referencing the amount we have through the molar mass, and that will give us an equivalent number of moles. So that's why we use moles. So we're going to figure this out by dividing the elements by the smallest value to get whole numbers for each atom. If we divided it by the largest number, we would get a fraction, and we don't want to work with fractions when we're talking about compounds. We want to do it in whole numbers. Okay. So I like to draw a box here. I would say carbon, hydrogen. Then I'll list the moles here, moles. And then I'll find the ratio here. I'll divide it by the ratio, and then I'll find ratio here, and let's just say we'll do moles, then we'll find I guess we'll say moles, and then mole ratio here, and then here we'll say the ratio in the formula. So this will be the ratio in the formula. Okay, so for carbon we have 6.2365. For hydrogen we have 24.8515. So the mole ratio, we're going to say divide this number by the smallest number, which is itself, 6.2365. And here we're going to divide 24.8515 divided by 6.2365. So that's our mole ratio, right? We're trying to find how many moles of carbon to hydrogen in the smallest, simplest ratio. And then we'll find the result of this in the ratio for the formula, which is 1, and then 24.8515 divided by 6.2365 is roughly 3.98. So this is roughly 3.98, but we're going to round this to 4. Okay? So when you get a situation where you're close to 4, or close to the number, like 3.98, 3.97, you round it. The only time you don't round is round down, or round up a lot by a lot. For example, if you have 4.25, you don't want to round down to 4, and you don't want to round up to 5. In that case, you'll have to do some more math to get it to a whole number. But that's another situation, and we'll do more examples of that later on. Okay, so that's the whole number ratio. So in our formula, it's 1 to 4. So so this will be, our ratio would be, we have 1 carbon and to 4 hydrogens. So if we use this ratio, our formula should be CH4, because we have 1 carbon atom in the formula and 4 hydrogen atoms in the formula. So that's what will be our empirical formula. Okay, so let's stop there, and we'll pick up again in the next video. Okay, see you then.